next talk is from Áine Byrne. Áine obtained her PhD from the University of Nottingham, where she also won the Andrew Henry Postgraduate Prize. She then worked as a postdoctoral research at New York University. Now she is currently an assistant professor in the School of Mathematics and Statistics in the University College of Dublin. In her research, she uses tools from dynamical systems and statistical physics to study how neurons synchronize and how this synchronization generates oscillations in the brain activity. So thank you for coming.
Thank you for the kind introduction and for the invitation to speak today. So today I'm going to talk about the work I've been doing for the last couple of years. It's going to be an overview of these type of models that I've been building. So brief outline, we'll just give an overview of some of the neural modeling, then talk about this quadratic integrated fire neuron model that I use and how we use this reduction to get what we call the next generation of neural mass models. I'll talk about some applications and some future work. And everything that I talk about today, well, not everything, most of what I talk about today is covered in this review article we wrote. I wrote with collaborators in 2020. So I think, yeah, it was actually published in 2020. So I actually put together this slide during Jonathan's talk because I thought it would be a good way just to link in what I do to what's being talked about by Gustavo and Jonathan. So they're talking about whole brain models where we have, we use a brain atlas and some sort of cartography to distinguish how connected brain regions are. So each of the kind of red circles here are brain regions and they're connected by green lines. And at each red dot, so in each of these brain regions, we have a model, some set of equations that describes how the activity in that area changes with time as the connection strengths change and things like that. So in my work, I look at these brain region models. So say inside of those red dots, we have another network, which is a network of neurons. So now think of each of those blue dots as a neuron, and the neurons are connected with different probabilities and different strengths. So each neuron has some equations that describe how its voltage evolves with time, how its the synaptic input evolves with time. And in my work, I'm trying to build mean field models that describe the average activity of that population, but starting with those individual neuron models and then looking at the average activity, and then those models could be put into the whole brain models as one of these red dots. So at every red dot, we have one of these mean field or fire and rate models, as they're often called. Okay, so everyone or anyone who's done any bit of mathematical neuroscience will be familiar with the Hodgkin-Huxley model developed by Alan Hodgkin and Andrew Huxley in the 1950s, where they recorded the electrical activity from the axon of a squid and used the laws of electrical circuits to write down a system of equations that very accurately described the propagation of an action potential. So how the cell generated these bursts of electrical activity and how it traveled along the axon. But when it comes to modeling brain areas, we're thinking maybe hundreds of thousands of neurons. Can't really have 100,000 sets of Hodgkin-Huxley equations. You need something a little more simple. And that's where mean field models come in. So we think about measuring with an EEG cap or MEG. You're measuring the average activity of hundreds of thousands of neurons, and the frequency of those rhythms depend on your state of arousal, which of course has been covered in great detail already today, so I won't go into details there. But the idea is to come up with a model that accurately tracks the average activity of the 100,000 neurons rather than each neuron individually. And this was kind of first done by, wasn't first done, was first maybe done famously by Hugh Wilson and Jack Cowan. They had the Wilson-Cowan model, which you may have heard of in the 1970s. And the idea there was they are averaging over heterogeneity or noise in the network. So you have lots of these neurons, and you can think of them as threshold units. They're either active or they're not active. And if you average over a population of these threshold units, you get a firing rate curve that tells you if the activity is low, so if there's not many neurons active, your firing rate is low. if all of your neurons are active, the firing rate's high, and then somewhere in the middle, you've got this kind of slope. So that's your sigmoidal firing rate curve. And they said, okay, assume we have two types of neurons, your excitatory neurons and your inhibitory neurons. And we just want to track the average activity of both these populations and see how they interact. And they say that the excitatory population is going to excite the cells it's connected to, i.e. they're going to become more active, and there's some coupling strength there. It talks to itself, but it also talks to the inhibitory population. So when the excitatory population is active, it's going to excite that inhibitory population. Inhibitory population does the opposite. It quietens down the neurons that it's connected to. So you'd imagine that this strength here, the WEI, so that's how strongly these cells are connected. These ones, that's going to be negative. It's going to drive down the activity of this cell, and it also they also drive down their own activity. And with that, they came up with two very simple differential equations that tell you how the average activity of each of those populations behaves. So if there is no input, so imagine, so this is f is a function of these input terms. So if there's no input, so that those two f's are 0, then you just get a minus e and a minus I. So the activity decays to 0. So if it's getting no input, this activity decays to 0. If it's getting some input, it's going to increase the activity. And there's a balance here. And what we typically find with these models is we get oscillations because the excitatory neurons excite, they turn things on, they turn on the inhibitory neurons, which then shut things off. And there's this cycle. And we can get oscillations at different frequencies. Plug something like this into your whole brain network model and look at how the whole brain activity changes, and how when different areas are oscillating at different frequencies, how these different oscillations interact. One of the components that I want to highlight in these mean field models or firing rate models that's often glazed over is the postsynaptic response. So here, the postsynaptic response is like the middle one. We get an instantaneous increase when something's on, and then it decays back to 0. You could have an instantaneous response, which would just be like a delta function. When a signal arrives, it's automatically just transmitted as a large burst of activity. And then the more realistic postsynaptic response is on the right there. So you get a gradual increase and then a gradual decay. And this is built into the model with your differential operator. So I said, if you go back to the equations here, you've got your minus e on the right-hand side. If you put that on the other side, you can imagine you're going to have 1 plus tau d dt all times e. So that's that q, your differential operator. And we can get our more realistic response just by putting it to the power of 2. And when what I do, we're going to use that more realistic response. Okay, and this is really, you can think of the postsynaptic response of an individual cell. It's just generalized to be the response of the population is modeled like the postsynaptic response of one cell getting one action potential or burst of electrical activity. So that would be, you could write the Wilson-Cowan model in the form QE acting on your variable E is equal to the firing rate. And that's the general form of a mean field model. Differential operator acting on a variable, it could be your the activity of your population equals to a firing rate. And the models that I derive will have this form, so that's why I just wanted to highlight it. Okay, but something's missing here. These models are built on the assumption that the neurons fire asynchronously. So to get that sigmoidal function, we've said that we have a network of these threshold units that are they're independent of each other. That's not the case. Neurons activity depend on the neurons that it's connected to. And many neural phenomena are results of neurons synchronizing their activity and then desynchronizing their activity, which is actually what motivated this work. And we wanted to look at event-related synchronization and event-related desynchronization. So we wanted a model that tracks synchrony at this mean field or population level. We need to go back and look at the dynamics of the underlying spiking network. So we have, say, a network of neurons. We look at their raster plot, so the spike time. So each dot is the time at which a neuron fires an action potential. And along the x-axis, you have time, and the y, the neuron number. So when you have kind of horizontal or vertical lines, they're like synchronous spiking events. You've got lots of neurons firing action potentials at roughly the same time. And then on the right, we've got our synchrony, and you can see that it is changing with time, and then also the firing rate. And so how many of those neurons are firing at any given time. You can see that it goes up, it spikes at times that will correspond roughly to when we have these vertical lines of red dots. So to build this model, we go back to the single neuron dynamics, and we're going to look at a much simpler model than the Hodgkin-Huxley. It's called the quadratic integrate and fire model, and it just says that the voltage of the neuron evolves quadratically when it gets some positive input, and then there's a threshold, and once it reaches a threshold, we reset it back down to its reset. And if you choose your parameters in such a way, you can get something that looks like an action potential. So it goes up quadratically, hits 100, and goes back down to -5, and you can rescale your voltage into, a true range of, say, -80 to 50 if you want, but same idea. And the frequency at which these action potentials happen is related to the square root of your input parameter here, which is eta, which you can think of as the excitability or the background drive. So the larger this is, the higher the frequency of oscillation is going to be. So we want to think about a network of these. So again, we're thinking about a small brain region. So we're zooming in on, say, just some random brain region. And we have a network of neurons all connected to each other. And each neuron has its own voltage dynamics. So it has subscript VI, and then they also all have different levels of excitability or background drives. Okay, and then you've also got a coupling current. So this II is the coupling current, and it's going to be in the same form of the kind of ionic channels in your Hodgkin-Huxley model. You've got a conductance, which evolves with time, multiplied by reversible potential minus this current voltage. And this is where the postsynaptic response comes in. So that conductance term is, you've got a differential operator acting on it, and we're going to use that nice alpha-shaped function for your postsynaptic response. You have a non-zero rise time and a non-zero decay time. And that's, you can think of as temporally filtering your spikes. So every time a neuron it's connected to spikes, you get a delta pulse, so just an instantaneous increase in activity, which is then temporally filtered. So it's this smooth postsynaptic response. And then that I goes in here and drives the activity of else that it's connected to. Okay. And you can set it up and simulate, say, 100 neurons, and you can get these types of raster plots where you have synchronous activity. You can also set the parameters so that they are asynchronous. In general, you're going to be choosing this background drive or level of excitability from a poled or a unimodal distribution, so it has a mean and a width. And if that width is sufficiently small, neurons are sufficiently similar, and you get synchrony. Whereas if the width is very wide, then you have a lot of heterogeneity in your network, and you potentially need strong coupling to bring them back into synchrony. So they're the two kind of parameters that are important in your synchrony. Okay, I'm not going to dwell too long on this, but the idea in my work, to get synchrony, we want to transform to phase. So instead of thinking of the voltage of the neurons, we think of where the voltage is in relation to the threshold and the reset. So you can think of, so here's a movie, so you think of transforming to phase. So you're going between, say, minus pi and pi, and every time the neuron spikes, so it goes through threshold, so on the right you've got the voltage trace, is when you go through pi in your phase variable, and then your phase evolves with time, corresponding to where your voltage is in relation to how close or far away it is from threshold. That's the main idea, and in doing that you can come up with a phase description. So now instead of saying dVdt equals something, i.e. the voltage changes with time, the phase changes with time. They're equivalent. And the main reason for doing this is so that we can look at synchrony. So now think of each of these colored dots being an individual neuron, which has a different phase. That phase is evolving with time. And if all of the neurons have the same phase, you can imagine all of those colored dots are going to be at the same point at the same time. And this black dot in the middle is your current motor order parameter that tells you how synchronous or asynchronous the population is. So right now, a lot of the neurons have similar phases. So that black dot is close to the edge of the disk, which means we've got high synchrony. And we think of synchrony being the magnitude or the length of this vector. Whereas now, you'll see in a second, the neurons have all very different phases. Say here, pause that. And that black dot is in the center. And there we'd say they're asynchronous. They all have very different phases. And the distance from the center to the dot is small. It's close to 0. So they're asynchronous. And that's what your current motor order parameter is just the sum of the exponent of I theta. So then when you add that up, if you get a complex number where the length of that complex number is your level of synchrony. If it's 0, they're totally asynchronous. If it's 1, they're fully synchronous. And if it's, say, 0.5, then they're partially synchronous. Okay. And with that, we can apply what's known as the Ott-Antonsen ansatz, which assumes a certain shape for the distribution of those phases, which has been proven to be the correct shape. And we use a continuity equation, and that tells us, the ansatz really tells us about the distribution of those phases. As z goes to 0, we have a flat distribution, they're totally asynchronous. As z goes to 1, you're going to have a very peaked distribution. And somewhere in between, we have a peak, but it's not a sharp peak. And the maths behind this isn't particularly important for today's talk anyway. Just trust me that it works. And if we apply this Ott-Antonsen ansatz, we get what we call our next generation neural mass model. And now we have a differential operator acting on our conductance variable. And that's equal to, say, our coupling constant times a firing rate. So the exact same form as the Wilson-Cowan model, only now this firing rate is a derived function of the current motor order parameter. So before it was a function of, say, the variables that the differential operator was acting on, but now it's a derived function of the order parameter that tells us how much firing we should expect to have, depending on how synchronous the population is, and also what the average phase is. So you could be synchronous, but not firing, because you could have all of the neurons with phase over here, so they're fully synchronized, but they're not going through pi, which is where we defined firing to be. So it's here, this is a surface plot of this function. So it's a real valued function of a complex number. And so the neurons spike when they go through pi. So that's the red high firing point there, but you still get firing even if you're not exactly at that point, because if you're, say, here, that means, say, 50% of the neurons are going through pi at that given time. And then we have, oh, that was just to show you that. So then we have also have a differential equation that describes how the synchrony changes with time. So that gives us, it's actually a set of 4 equations, because you've got your order parameter is complex, so it has real and imaginary parts. So that's 2 variables. And then we've got our firing rate equation, and we chose a differential operator that was second order. So that will give you 2 equations. So 4 equations. And if we run a simulation of 100 of these quadratic integrating fire neurons with all the same parameters, and then also use our mean field model, we get a really good fit. So this is 100 neurons, and this reduction is exact as the number of neurons goes to infinity. But you can see here with 100 is the red trace, and the mean field is the blue trace. They match relatively well, so that's your order parameter. It's real and imaginary parts, and then here is your conductance and its derivative. And again, if you increase the number of neurons, you increase the goodness of the fit. The main idea here for only using 100 is to show you that there are some finite noise fluctuations there. I think even with 500, they match almost exactly. Okay. And the first novelty or benefit of this model is that we have this conformal mapping. So even so we went from our quadratic integrating fire that tracked the voltage to the theta neuron that tracked the phase. And then in the mean field, we track the synchrony. But there's also a mapping to go back to that voltage framework at the mean field. So this is work by Montbreo and Pazzo. So if you're familiar with their mean field model, they're equivalent. There's just this mapping that tells us then how you still got your conductance equation, just second order, and then you've got a equation that tells you how the firing rate evolves with time, and then you've got an equation that tells you how the voltage evolves with time. So they're the same model, just posed in a different way. And we can do things like a bifurcation analysis, so I won't dwell too long on this, but the main idea is with a single population, we can get oscillations, which is not possible with kind of your traditional mean field models. So your traditional mean field models, you need this interplay of excitation and inhibition to get oscillations. Whereas here we could set up, say, an inhibitory population, so just inhibitory neurons, and give it some external drive that's uniform in time. It's not going to be temporarily oscillating. And we can find half bifurcation. So half bifurcation tells us on one side of the bifurcation, we get oscillations, so the activity fluctuates with time, and on the other side we have a fixed point, so it just decays back to a certain value. And this diagram here is varying two parameters. So this is eta naught is the mean of our background drive, or excitability, so that eta parameter, that's the mean of it, and then the delta is the width of it, so it's the heterogeneity. So you can think of increasing delta increases the heterogeneity of your network. Whereas increasing eta naught increases the average firing rate of the network. And each of these curves is for a different coupling strength. Increasing, so red is coupling strength 1, there's 2, 3, and 4. And below the curves, we have oscillations, and above the curves, we don't. That's the idea there. So if you had your coupling strength equal to 1, then for all of these parameter values, you can see oscillations in the average activity, whether that be your order parameter, your firing rate and voltage, and increasing the coupling strength, you increase the area for which you get oscillations. Then when you couple two populations, so more traditional kind of thinking of firing rate, the Wilson-Cowan models, you've got an excitatory population and an inhibitory population, and they're coupled together. You can get more kind of complicated bifurcations. So for any mathematicians, you get period doubling bifurcations, you get isolated torus bifurcations. So there's lots of interesting dynamics that one could explore there. Okay, but in terms of real applications, the first one I'm going to talk about is beta rebound, which was really what we were trying to model when we developed this model in the first place. So with colleagues in the Centre for Brain Imaging in Nottingham, they're interested in something called beta rebound, which is the phenomenon related to movement. So if you are static, if you're not moving, you'll see oscillations in the beta band, so between 13 and 30 hertz, coming from your motor cortex. In the same way you'd see alpha rhythms when you have your eyes closed in the visual cortex. And then when you start to move, the amplitude of those oscillations dies out, so you'd see a reduction in power. And then when you stop moving, you get a rebound in that power. So the oscillations come back with a higher amplitude before decaying back down to their original amplitude. And beta rebound is used as a biomarker for schizophrenia. So schizophrenia patients, they get the reduction in power, but their rebound is much smaller than for healthy controls. So if you look at your spectrograms here, you see when the subject is moving, you've got your decrease in power. So these are relative spectrograms. Dark blue is a reduction in oscillatory power, and then orange, red, yellow is an increase. And you can see you get this strong red spot here for your healthy controls, whereas for your schizophrenia patients, that rebound or increase in activity is much smaller than for the healthy controls. So we were interested in developing a model that could somehow link synchrony to these changes, because this is also referred to event-related synchronization and desynchronization. Without any real evidence, we can't actually see what the synchrony is of the network of neurons underlying this. This is MEG data, sorry, I forgot to say. So we set up the model with its parameters in such a regime that it oscillates at 13 to 30 hertz. So you're going to have, I'm going to press play in a minute, and this figure on the right is the order parameter for the model. And you'll see that there's a limit cycle, i.e. it's going to be changing with time. So this is it, say original, you're not moving, and then you switch on a signal that corresponds to maybe a motor signal, and you get a smaller amplitude, that's actually higher frequency oscillation. And then when you turn off the drive, or that kind of motor signal, the order parameter goes to the edge of the disc. So remember I said the edge of the disc is high synchrony. So that's without any, all we've done there is turn off the motor signal. And you're driven to the edge of the disc before spiraling back to the original behavior. Importantly, this is a 4-dimensional model. So this is just showing 2 of the variables. So that's why we have this kind of unexpected move to the edge of the disc, because one of your other variables is far away from its steady state, and to get back to that activity, it has to edge of the disc. Okay, and then if you look at the spectrogram of your synaptic current, which we think of as somehow being related to the MEG activity, you see that you have power at around 15 hertz. There's a reduction in power when that motor signal is turned on, and then there's an increase in power after it's switched off. So in that way, we were able to link these kind of changes in the observed spectral power to changes in the level of synchrony in the underlying network. And in a follow-on study, we looked at trying to identify what it was that increased this power or decreased that power of the rebound, and we found that the synaptic timescale was important. So if we, I can't remember now off the top of my head if it was increased or decreased, the synaptic timescale, i.e. how long it takes, say, one individual delta pulse to be go through your synapse, that changed the power of the rebound. So somehow linked the schizophrenia study in there, that maybe synaptic timescale is something to look into. Another important thing that we were looking at is, this should say beta burst, not beta rebound on the title, is something that I only became aware of in maybe the last 5 years, is that neural oscillations are not steady and sustained. So when you see a, say, spectrogram like this, it's trial averaged. And if you look at individual trials, there are bursts of, say, frequency in the beta band at individual times. Even if you're just looking at resting state data, you see bursts of activity rather than a real increase in activity, say like here. So this is something you might see, a trial averaged. You've got spectral power in the beta band. But if you look at the individual trial, you just see a spot. But because you trial average, there's spots at different places across many different trials, then it looks sustained in the trial averaged behavior. So that was something that we were interested in investigating, and we were able to reproduce it in the model. So this is actually, these are model results, not data, where we set the model up close to, say, a bifurcation point, so that and then had noise driving it. So some of the time it's close to, well, actually it was at a fixed point, but then when you give some noise, it temporarily will shift over the other side of the bifurcation, and you get oscillations, and then it dies back down, and that gives you this bursting type behavior. And we are able to match the kind of length of the bursts, the frequency of the bursts, and the power of the bursts to MEG to MEG data, and show that the model quite accurately produced these. And in a follow-on study now, we're looking at how the duration and power of these bursts is implicated in Parkinson's disease, and trying to understand the parameters that are important for that reduction in the power of the bursts. And also, I think they tend to be longer in Parkinson's patients. Another thing that I started looking at is epilepsy. So in the system, we can see coexisting limit cycles. So for the same values of parameters, you can have different oscillations. So here on the top is what might be healthy activity. You've got regular increases in your firing rate. And then in the middle, you might have some sort of spike wave bursts that are like epileptic behavior. And if you start the model in this regime and just give it a small perturbation, it can enter this unhealthy seizure-like behavior. So again, in this work, we have been looking at the basins of attraction of the states and seeing what kind of perturbations you'd need to say then transition back to the healthy state once you start, once you transition to the seizure-like state. Okay, this is just, again, giving you an overview of all the different types of things that we have done or can do with the model. So the other one is probably more similar to the work that was talked about already. So looking at functional connectivity from structural connectivity. So now we're thinking we have our whole brain atlas, and at each node, we're putting one of these next generation neural mass models. I think it's a 72 brain atlas, so we've got 72 populations of neurons, and we have a structural connectivity matrix, and we can get out then a functional connectivity matrix. And one of the things that Michael, who is a PhD student in Nottingham, was doing was looking at transcranial magnetic stimulation, so TMS, so applying it to different brain regions and seeing how it affected the network structure. So I didn't put it in. So there's a nice table in the paper that shows how each of the graph theory measures changes depending on where you stimulate. So kind of the eigencentricity and the number of, I always forget these, the number of nodes that are connected in the functional space. And there's all these different measures of your network structure that change depending on where you stimulate with this TMS. So again, it's kind of exploratory work. We haven't really dove into what it means in terms of treatments for different disorders, but that is scope. That's, that can be something that can be done in the future. I'd be happy to talk to anyone if they're interested in that type of thing. And then this is the last kind of piece of work that has been done. Then I want to talk about two upcoming pieces of work. The nice thing about this model is that there's a link back to the individual neuron model. So you can put in cellular level mechanisms and then see how they translate to the mean field or the population level. So for example, we looked at including gap junctions in the model. So in a realistic way, you're just thinking about gap junction. If two neurons are gap junction connected, they're exchanging voltage. If one is high and one is low, the current going to go to the one that's low and decrease its voltage, and then increase its voltage and then decrease the voltage of the high one. So they've got some mathematical expression for your gap junction, and you can do your whole mean field reduction again, and you just get these two additional terms in your description for your order parameter. Or if you look at the firing rate voltage framework, you just get one additional term that tells you how that gap junction affects the mean field dynamics. And then you can study how changing the strength of that gap junction is going to affect the overall dynamics. Okay, so just to finish off, I wanted to talk about two pieces of work I'm just starting on. So the first is with Amar Ali in relation to Parkinson's. So he has been looking at deep brain stimulation in Parkinson's, but using large networks of interconnected neurons. So using, say, your Hodgkin-Huxley or its Cavich neurons, and stimulating like hundreds or thousands of individual neurons. And, very computationally expensive, but you can reproduce the response that is seen in the brain to deep brain stimulation, but you can't gain much insight into why it's working or what exactly is happening. So the idea is to replace each of the subtype of neurons with a neural mass model. So we've got, say, different brain areas, and then within each brain area, you've got different neurons. So recently, the next generation neural mass models have been extended such that instead of using the quadratic integrate and fire model, which kind of the only parameter you have is to change the frequency, you can instead use the Cavich neuron model, which is a lot more parameters to change the spiking regimes of the neurons, so you can have different types of neurons. So we can come up with a setup where we interconnected types of neuron populations and hopefully see the same results that Ali was seeing in the large network, and gain a bit more understanding into why deep brain stimulation is working, and what if we want to do closed loop stimulation, how we might be able to do that. And yeah, so then I think that's just showing some of his results. So when you deep brain stimulation off, you get too much power in the beta band in Parkinson's patients, and then when the stimulation is on, you have a reduction in that power of the beta activity. So hopefully we'll be able to understand a bit more why that's happening and which neurons are playing the most important parts. And then the other piece of work that I'm starting on now is with Mark Cunningham on epilepsy. So Mark has unprecedented access to human brain tissue. So this here is actually a picture of Mark on the first day that they did experiments. In Beaumont Hospital, they're resecting tissue from patients with epilepsy, so resecting the part of the brain that's causing the seizures. And in a new collaboration Mark has with Beaumont, he's now using that tissue for research purposes. So there's the trace. They've put some electrodes on the human brain tissue, and you can see we get some sort of spike wave activity like a seizure. So that was the first seizure recorded in human brain tissue outside the brain in Ireland earlier. It was last year. It was October of last year. This type of work has been done elsewhere. So in the UK, so that's on the right from Jones et al. In 2016, where they had human brain tissue, and they're looking at the propagation of a seizure, and kind of got different, when you bandpass filter the activity, you get different types of oscillations. So you've got high frequency here. Then if you filter it down, you get some spike wave behavior. Actually, that's a lie. This isn't. This is actually different times of the seizure. Yeah, sorry. So you get your spike wave towards the end, and you've got your high frequency here just before it starts. So we're going to, again, look at developing these mechanistic models to understand particular things. So one might be gap junctions. Gap junctions are believed to be important in epilepsy. So we're going to see how gap junction coupling can affect these seizure dynamics. And also more recently, it's been shown that the AMPA receptor, which is believed to be very fast, actually has a slow subcompartment. So we're going to explore that also in the model. And because we have this link between the cellular level model and the mean field model, we can really look at cellular level mechanisms at the mean field kind of population activity and see how they affect population dynamics. Okay, so just to summarize, these next generation neural mass models, well, myself and my collaborators think they're great. And they support oscillations in a single population. We can now track synchrony at the mesoscopic or population level. We have a link between firing rate and the underlying spiking behavior. We'll be able to reproduce certain things like the beta bursts and the beta rebound, and we can map the cellular level processes to the mesoscopic level. And there are many exciting applications and extensions to come. So to finish off, just acknowledge some of my collaborators. So Steve Coombs, who was my PhD supervisor and I continued to work with. We've got Ruben O'Day, who's an assistant professor in Nottingham. Michael Forrester, who was a PhD student. Michael Forrester and James Ross actually were both PhD students with Steve, who've both gone on to industry, so they're lost. And Matt Brooks, who does MEG in Nottingham, and then Rachel Nix, another assistant professor in the School of Maths. So with that, I'll say thank you, and I'll take any questions.
Thank you. Do you have any questions?
Yes. Thank you for the talk. I have a question about the role of the noise. If you include noise in some point of your model,
yeah, so I think so in the beta burst work, we were using noise. So we're including think it was pink noise. I can't actually remember. So that a lot of the noise work was done by James, but it was putting noise in again at the mean field level. So you can people have looked at putting noise in at the single neuron level and translating that back as through the mean field, and there's kind of a lot of mathematical work on that. But from our side, we just said, okay, well, what if we hypothetically put in noise at the mean field level and see how the system transitions? Again, we said with close bifurcation, so we're transitioning between oscillations and fixed point. Yes, I mean for the
Thanks. I was very happy to see you include phase, but I think I continue on that question about phase, and because of role of noise. If you would go to a conductance-based modeling instead, then you have this possibility. You have all the changes in current or in potential, and then you can get the jittering of spikes essentially from noise sources on current or potential. So how sensitive are the results with regard to the single neuron noise on, let's say, phase?
I would say the general results are not dependent on the noise, but if you want to look at, say, specific spike timing and but in general, because it's such a large number of neurons, and you're thinking synchrony, firing rate as an average, jittering kind of spike times very slightly. I can't imagine it changes the overall dynamics very much. But it is, again, not my area of expertise, but people have definitely looked into the sensitivity of these kind of reductions to noise and different types of noise.
Can you add? Yeah, thank you for the nice. Can you add some heterogeneity in the weights? Like you give a a distribution instead of because here you get the same weights like mean field in the sense it's like homogeneous connection.
So we include heterogeneity in terms of the excitability. So each individual neuron has a slightly different kind of frequency that it likes to be close to. But you can also put the heterogeneity into the coupling strengths. The one thing is that, again, I usually gloss over, is one thing you have to assume when doing this reduction is that you are all-to-all coupled, but you can then put in, say, a distribution of coupling strengths so that some are weaker than others. You can put in any number of heterogeneities. The problem is you get a new order parameter for every set of heterogeneity. So if you put in heterogeneity into your coupling strength and into your background drives or your excitability, you're going to, and then maybe something else, you get an additional order parameter, which is an additional 2 equations per population that you're looking at.
I have a question also, like when you say your future work will be to see like epilepsy, how these events propagate, how are you planning to go to the the space dimensions with these kind of models? How do you couple them?
Yeah, so we actually have done work on neural field models, which is spatially distributed systems, which I haven't really talked about, but you can do the kind of similar thing to, are you familiar with standard neural field models, where you have a coupling function that is somehow space dependent? So you can put that into these models and look at that also. But in terms of the epilepsy work with Mark, we really are trying to think of all of the important mechanisms at the cellular level that play a role in the generation of the seizure, and then see how they map to the mean field or population activity. So that's kind of the starting point of that work. And then maybe with time we can think about spatially distributed fields.
There's so the beta rebound is rebound, but also alpha activity, for example, change at the same time, or mu how it's called there.
Yeah.
And this is actually seen quite often. There's also things like delta theta coupling, right?
Yeah.
How would you So it suggests that it's also physiologically relevant to look at frequency coupling across different bands. How would you embed that in your model?
So to look at multiple frequencies, we really need to be considering more brain regions. So I think the way to think of it is these neural mass models, that they're an individual brain region and they can oscillate at a particular frequency. And then if you couple it to another brain region, you can start to see interactions of frequencies, and then also the frequency and the coupling strengths, which is work that has been done by Priyesh Tiwari. He's in Amsterdam, and he's kind of looking at a lot more of this kind of functional connectivity, structural connectivity, and functional connectivity in the sense of that kind of theta coupling and gamma coupling and things. So I can give you some references if you want to look more at it.
Essentially, I would say as long as you have a single area, they only always resonate at a single frequency.
Not actually, that's probably not true, because in the way we set it up, yes, but if I go back to, so these kind of bifurcation diagrams, in the very left or very rightmost there, when we have torus bifurcations, there's a lot more multi-frequency oscillations there that we haven't really explored in that sense. But now that I think about it, that is true, that there you can get multiple frequencies in the same for the same population, that there's some sort of overlaying. You can kind of see it there, that you've got a slow rhythm and then it's kind of faster rhythm within it. So that's possibly something for future work.
Thank you.